Hello, good morning, and I told you I'd make a video on the solutions to the questions you did yesterday. These were paper 2 practical style questions. You've not seen many of these, if any, and they're a bit different. They're a bit fussier on significant figures. They use the percentage uncertainty stuff you were looking at last week, and in general they're quite hard and a little bit difficult to understand. So I'm going to give you the what I think are the easiest ways of doing these without trying to make this too long. So you need the document in front of you. I can sort of quickly show you the screen, but it's not going to be incredibly clear. That's the first question we're looking at. Remember, is this air track glider. It's going to glide down that ramp. It's got a piece of card and 2 light gates attached to it. Now the idea of this to get a value for G, which is different to the experiment, pardon me, different to the required practical experiment. That's always the case with these papers. The idea here is that if you can measure the difference in speed, then the difference in speed over the time taken for that difference gives you the acceleration. Now, how does a data logger do that? Well, just some of you may know this, so apologies if I'm teaching you something you already know. If there's a certain length of card attached to this trolley as it goes past, you imagine this sort of iPad is the light gate. If my iPad, my computer, knows the length of this card that's going through, and it times how long it takes to go from here to here, then it can use both the distance and that time to work out a speed. That's not an instantaneous speed, but it's an average speed over just that little bit of the ramp, so we can treat it as sort of an instantaneous speed. And of course we're given 2 sets of data here, one at light gate A and light gate B, and because the glider is going down a ramp, we actually work out that it takes less time to go through the second light gate because it's travelling faster. So looking at your document, question 1 gives you all of that info, although it doesn't explain the information as I have. It just tells us that it takes less time to go through the second light gate. You need to know why. It also tells us the time to travel from one to the other. So the first question, we're just asked to determine the acceleration. So you're going to take the time taken to pass through the first gate, okay, and knowing the distance of the card, you're going to divide the distance of the card by that time. Speed is distance over time. Make sure your distance is in meters. So it was a 10 centimetre card, so 10 times 10 to the minus 2. You divide that by the time to go through the first light gate, which was, so I'm scrolling down, 0.5. So we've got 10 times 10 to the minus 2 over 0.5. And you get a velocity at the first one of 0.2 meters per second. Same method for the next light gate. It goes through that, as we'd expect, a bit quicker, at 0.25. So what we're doing then is working out a difference in that speed. So 0.25 minus 0.2, and the difference in the speed divided by the time taken, which is given in the table as 1.19. Okay, gives us an acceleration of, where's their final answer? Let's type it in if I can't see it. They're giving us multiple ways of doing it, that's why I can't see the answer. 4.2 times 10 to the minus 2. That is in meters per second. Okay, so that is meters per second, should I say. That is our acceleration, our answer for the first bit. Now, we only want 2 significant figures there. They are going to penalise you if you don't. Everything, or should I say the least accurate pieces of data in the question are given to 2, so your answer should be to 2 significant figures as well. Next part. Now my computer seems to freeze up every time I leave it on this document, so if I'm faffing over here I'm just waiting for it to unfreeze itself. There we go. Then we're given 2 further sets of readings. They're called them set A and set B, and you are asked to establish, assuming that the ramp is the same and therefore the acceleration is the same, You're asked to establish why you can tell from that data that the light gates in set B are set further apart than they are in A. Numerous ways of showing this. If you are looking at your document now, I would suggest that you wrote here, remembering we're looking at 2 marks, that for a start the time to travel between the 2 light gates is much longer for set B. Now that alone is not going to be enough, but the fact that the time is longer, and actually as it goes through the first light gate it is travelling faster than it is when it goes through the first light gate in set A, okay, that would suggest that they are further apart. You could just work it all out using speed, distance, time and acceleration equations and just work out the distance between the two. You've got the time it takes to get from one to the other, you've got the speed at each one, and you know the acceleration from the first question, so you could quite easily work that out as well, if you didn't want to do it using the wordy sort of quantifying method. Next part, so that was part B. Part C, we're now given a graph, and this graph shows us that what they're doing now is they're placing some blocks underneath the ramp. And what we mean by that is just draw an exaggerated one. Okay, they're just placing some blocks underneath it to make it obviously steeper. Each of the blocks are the same. What the graph is showing us is the variation of the acceleration, and as we'd imagine, the acceleration gets greater as the number of blocks get greater. The first thing you have to do here is draw a straight line of best fit and determine G. Now, this is hard for me to show you whether you've done this right, but obviously a line of best fit should have an equal number of points above and below. It turns out that the best line on this one does go through the first point and the last point. What other advice have we got here for C? It goes through the first and last. Right, things they're fussy about. I'm reading from the mark scheme. The line must not be thicker than half a square. The line must have no breaks. The line must only be drawn once, so none of this kind of going over your line again and again business. You will lose marks, they're really fussy about that. If you do all of that, the range they are accepting is between 0.042 and 0.053. Just in case you are checking your answers against that, you can pause that and check that. So that's the gradient range that they're accepting when you've drawn that line on. You also need to show, just clean some space here, you do need to show you're working when you're doing gradient questions. One of the marks is for that, so the general general method you'd use for doing that is to make sure you show the triangle that you've used. You've done this data divided by this data, okay, so mark that triangle on there. What do we want next? We're given an equation here. It can be shown that for the apparatus used, the value of G, gravity, is equal to 2G over H, where H is the thickness of each block used in the experiment. Now, remember, our value for G was the gradient of our line. And so let me just write out the equation they were using there. If somebody came into the room there to disturb me. So the equation they've given us, just in case you're not looking at your copy of the document, was this. Don't get the two G's confused is what I'm saying. This is the acceleration due to gravity. This is the gradient of your line. They've asked us to calculate H, so we're going to use our gradient. Now remember, if you get the wrong value, you can have an error carried forward here. I've already said what the value should be between. But using your value of gradient, let's scroll down to the right answer here, we would be dividing, what are we on, part D, by 4.9. it says, of course, if you divided your incorrect gradient by 4.9, that would also be okay. Actually, just looking for their final answer here for this one. It doesn't give one because it accepts that your gradient value is going to vary. So as long as you've got your G value divided by 4.9, we could quickly work that out here. Let's just say we did get 0.042 for our gradient, and we divided that by 4.9. We would get 8.57 times 10 to the minus 3. Yours is going to be different if you got a different gradient value, but only penalise yourself once for that wrong gradient value. Part E asks you to explain without drawing another graph whether the data suggests that A is directly proportional to N. Right, easiest way to do this is get a value of A or N and make sure that on that graph you can see where that value doubles. And essentially, if A doubles at the same rate that N doubles, or halves, okay, or 3 times, it doesn't matter, that shows a constant ratio, and that proves that the two are directly proportional. Okay, so we take 2 points on our line. That's important. Not 2 of the points we've used to draw our line, but 2 points that fall on the line. And we say, okay, at this point A is, I don't know, 2, and at this one it's 4, and look, N was 4 and now it's 8, so they've both doubled going from one point to the other, and that shows that it's directly proportional. And that's only 1 mark for that one. Scrolling down. Ooh. It's freezing on me again. We are now on to the next question. This was the harder one. This was the roller that sort of, the ball bearing fell from here as that fell down, and the ball bearing hits it at a certain point and leaves a mark on the paper. Now we're using pressure sensitive paper here. We could just be using, if we were to do this experiment, the actual thing that dropped might not be a ball bearing, it might be something that's actually made of pencil lead or something else that's going to leave a mark. It might be dipped in paint or something and just leave a mark on the paper. How do we know they both go at the same time? Well, because of this clever idea that the ball bearing is held on a piece of string, the same piece of string that the back of the bar is held up by. The match burns the string, and so they both start at the same time. Now I won't read the entire thing out because I'm sure you've got the paper in front of you, but I'm just trying to answer the sort of questions I got from you by email. The first bit, we are asked to mark on the distance that the student should measure in order to determine the initial position of the sphere on the paper. And for this one, what they want is a clear identification of distance from the centre of the sphere to the right hand end of the mark. Okay, so you're going from the centre to the right hand end of the mark, because of course that's where it first hits the paper. The rest of it's just kind of a smudge. So I don't think many of you have got that particular bit wrong. We're then given a load of times, because the student does this quite a few times and measures that distance from where the sphere starts to the right hand end of the mark, and they get several different values. We're also told that the time that the bar would take to swing, if you just let it swing for 10 oscillations, would be 15.7 seconds. Calculate the time for 1 oscillation, and hence the time t for the bar to reach the vertical. So first, for 1 oscillation, well, we've got the time for 10, so we're going to divide that by 10 to get 1, so that's going to give us 1.57. That's easy enough. The time to reach vertical though, well, this is a bar that's swinging like this. A complete oscillation would be that. I'll do that again. That's 1 complete oscillation. That's what we're saying takes 1.57 seconds. So to go vertical, that is a quarter, right? 1, 2, 3, 4. That's a quarter. So we want a quarter of 1.57, and for that in terms of the accuracy of that answer. Let's just go back down. They're looking for that to 3 significant figures because that's what the data's been given. And it was 0.393 seconds, 0.393 seconds. Moving down. Determine the percentage uncertainty in the time t suggested by the precision of the recorded data. So we're going back to the thing that we have recorded here, not what we've just calculated, which was 1/4 of 1/10 of that value. What they recorded was a time of 15.7 seconds. How do we work out a percentage uncertainty for that? Well, first we have to look at the precision. The fact they've written 15.7 suggests that the precision was 0.1. Okay, 15.7, remember I told you in class, it's the smallest number you could fit into those spaces. So the fact they've just got 1 decimal place, the smallest number we could get is 0.1. How do we work out a percentage uncertainty? We do the uncertainty of 0.1 divided by the value times 100. And when we do that, we get 0.64%. Let me just quickly write that out for those of you who are not so good at just keeping up with me saying it. So that's our uncertainty over 15.7 times 100 to get it as a percent, 0.64. This came from the fact they've written the number like this. Okay, this is the smallest number that could go into these spaces. That's the uncertainty. Uncertainty over the value times 100 gives the percentage uncertainty. That percentage uncertainty would be the same for 1/4 of that, which we worked out, for half of that, for any fraction of that, it's a percentage. Okay. The next question seems pretty simple. There is a catch, as you might imagine. You are asked, just waiting for this to scroll down, you are asked to calculate a value for D. Well, we've been given 6 different values for D in that table. Do we just choose one? No, that's the student repeating the experiment. Why did he repeat it? So that he could take an average. Can we just take an average of those values? Look down them now if you didn't spot this yesterday. They look pretty similar other than the value of 0.701. Clearly an anomaly. There's nothing like the other values. So what they're looking for there is to take that one out and work out the mean of the other values. When you do that, you get 0.759. I'll just put that in a box there. Okay, so that is your answer to part D. Part E asks us to calculate the absolute uncertainty in the value of D. What does that mean? Well, that just means the uncertainty. So we're not going as far as the percentage uncertainty, we're looking at the uncertainty. Before, come back up to this, we said the uncertainty was the smallest value I could fit in here. Well, that's just because I'd only taken 1 reading. And in that situation, that's the only information I have about how accurate that reading is. When I've done a variety of them, I can clearly see from that table that the uncertainty isn't 0.001 because the readings vary by much more than that, so it's clearly much more uncertain. And so this is where we use this rule of half of the range. So ignoring the anomaly again, or if you don't penalise yourself again, okay, but you should be ignoring it. Biggest value, take away smallest value to get the range, and then halve it. That would be your absolute uncertainty for D. And the value you get when you do that is 0.013 meters. And that should really have a plus or minus in front of it because it's an uncertainty. Okay. Which I didn't do earlier on my other one. Determine a value for G and the absolute uncertainty for G. Now this bit is difficult because you can scroll up and down all you like It doesn't tell you how to work out G. So how does that relate to this experiment? Well, this is something falling. This is where this is similar to the experiment you looked at, dropping the ball bearing and using the pressure sensitive plate, the one we looked at the other day. Essentially, this is Suvat. This equation here. We're trying to work out G, which in the Suvat equation is A, of course. The ball bearing isn't moving at first, so I can forget that bit there. That's 0. So I've got half times G. This is T, which we know we have values for. And S, we also have values for. So actually, for this one, I'm confused with all my various different whiteboards now. We're going to end up with rearranging this, our G value, or our A value if you're using the Suvat notation, being equal to 2 lots of S over T squared. That's the rearrangement of that one. Now to put that in the context of this question, S is actually called D here, isn't it? And A we're calling G, so it's the same thing, just with different letters. So that's what we should be using, and that will get you 1 mark for this question. Because there are 2 for the first bit. It doesn't make this clear on the question. There are 2 for working out a value for G and 1 for working out the uncertainty. So that's the equation we're going to use, and when we put the numbers into that we get 9.83. So I'd imagine this is probably where most of you started to get stuck, so it was just using the Suvat again. How do we work out an absolute uncertainty? Well, this does get more complicated now, because we've got uncertainties in T, which we worked out earlier. That was the one we did, just looking at the number itself and saying the precision must be the smallest number we can fit in those spaces. And we worked out percentage uncertainty from that afterwards as well. And then we had this uncertainty in D, which we did from half the range. So how does that all affect G? Well, essentially, this here, okay, the uncertainty in D, we need to add that to 2 lots of the uncertainty in T, because T is squared, so that's like having T there twice. So we're actually looking at answers we got previously here. Our percentage uncertainty for the distance was 1.7, and our percentage uncertainty for the time that we worked out right at the beginning was 0.64, so we need 2 lots of that. Let's write this on a blank whiteboard. Oh, I don't have one. Make some space. At least then you can make a note of this and pause it and have a look if you still don't get where I'm coming from here. Put that in brackets as well. Percentage uncertainty in D, sorry, 2 lots of the percentage uncertainty in T, and that gives us 3% overall. It's asked for the absolute uncertainty in G, so why am I working out the percentage uncertainty? Well, because we can only add percentage uncertainties together if the 2 quantities are different. Once I've done that, I can then work backwards and work out the absolute uncertainty. And if percentage uncertainty is calculated by doing the uncertainty divided by the value, okay, the uncertainty divided by the value, then to get the absolute uncertainty, I need to look at the value I've got here, which is our 9.83. And if I divide my 3% by 9.83, I get 0.3. So that would be my absolute uncertainty, would be 0.3 meters per second squared. So start with that, work backwards. Always add percentage uncertainties together, and remember, it doesn't matter whether you are taking one quantity away from another, adding them together, squaring them. Every time you introduce that letter again, that quantity again, you're adding another one of its uncertainty to your final answer. So, you know, in that question, we had d divided by t squared, but I didn't divide d's uncertainty by t's. D was in there, t was in there, and it was in there twice because it was squared, so they were all added together. Pardon me. Where are we now after waffling? We're on part G. Discuss one change that could be made to reduce the uncertainty in the experiment. Use something pointy rather than a sphere so it left a clearer mark. That would be an obvious one. Time more swings of the bar to get a better idea of the time actually taken to return to vertical. Especially as one of them was an anomaly, so we actually discounted that anyway. And you should say why you would do that. You would take more because having more repeats reduces the percentage uncertainty. I must use the right words, okay? It reduces the percentage uncertainty. A longer or heavier bar, not something I would expect you to come up with, but just in case you ever come up with a similar question, a longer or heavier bar would have a bigger time period. It would go much more slowly. That would reduce the uncertainty and therefore the percentage uncertainty in your measurement of the time as well. Moving on from G. Computer's frozen again. I'm not having fun with computers today. That's something wrong with my connection, I think. Right. Last bit. The student modifies the experiment by progressively shortening the bar so the time for an oscillation becomes shorter. They collect data of distance fallen and corresponding times. Suggest giving a clear explanation how these data could be analysed to give a value for G. Well, sort of rearranging the equation we had before, really. What we would want to do here, and this is only for 3 marks, so it's not a full describing a practical. Let's just make a quick note of the equation we're using here so I can show you why we're going to do this graph. What we know is that if we get rid of that ut bit because it's 0, s is equal to half at squared. And so actually, remember a is g, let's change that in the context of this question. A is g. If I want to work out g, then I could plot a graph of s against t squared. S against t squared, that would give me half my g value, and then I would need to multiply that gradient value by 2 to get a g value. So that would be 3 marks really. Write the equation out, suggest plotting s against t squared, and then suggest doubling the gradient to give you a value for g. So not the nicest questions, probably one of the reasons we leave them till the end of the year, because I don't like doing them either. But you're going to have to do them in your exam next year, unfortunately. And hopefully you'll get more of the actual practicals done next year as well. Any of that didn't make sense, then email me and I'll get back to you. See you later.